Hey everybody. So we're going to continue looking at how we've been kind of dancing around how derivatives can inform us about the shape of a graph. We're going to dig a little deeper into that. But I want to remember a couple of things that we learned in some previous videos with the mean value theorem and some other things. The first one was, one of the big ideas was that if we have extrema, in particular, let's say local extrema, this means local maximums or local minimums, these happen at critical points, right? So critical points or critical numbers, these are the places. I like to distinguish, and every book does this carefully. Critical numbers would be the x value, critical point would be the coordinate point. That's at least what I'll use when discussing these. So local extrema will happen at particular x values. These critical numbers are at the critical points associated with them. These are places where the derivative doesn't exist or the derivative is zero, right? So we know that we need to look at local, that we can look at critical points. I don't know why I can't draw this line straight. For local extrema. However, we need to be careful because just because we have a critical point does not mean we necessarily have local extrema. So the location of local extrema must be critical points, but critical points do not need to be the locations of extrema, right? So we need a way to tell when we've got a critical point, well, is this actually a local maximum or a local minimum? That's what we're going to work on here. One of the other previous ideas we discovered that we're going to use in this section from the mean value theorem, we found that if the value of the derivative is positive, then the function is increasing, right? So if you have an interval where the derivative is going to be positive, then you know that the function's increasing over that interval. And in a similar way, if the value of the derivative is negative, the function must be decreasing, right? Is this fairly intuitive if you've been absorbing the idea that the derivative tells us about the rate of change? If the rate of change is positive, changing the input leads to a positive change in the output, that's an increasing function, right? Or the slopes of the tangent lines are heading up, so the function itself must be. We proved it with a little bit of algebra and reasoning, but I think that intuition is pretty good for holding that idea. So there's some of the ideas we're going to use from our previous work. So let's look at a function and then see how we can use these ideas to determine whether a critical point is actually a local extrema. And in particular, which kind of local extrema is it? So let's start with this function. F of x is going to be 3/4 x to the 4th minus 2x cubed. Okay, degree 4 polynomial. I'm going to look for its critical point. So I'm going to take a look at the derivative. F prime of x will be 3x cubed minus 6x squared. And I want to find, first of all, it's a polynomial, so it exists everywhere. So remember, critical points where the derivative doesn't exist or where it's equal to 0, it exists everywhere. So our only option for critical points or critical numbers is when f prime of x is equal to 0, right? The solutions to this equation will give us the critical numbers. So this equation can be written as this, factor out 3x squared, we're left with x minus 2. So we have two possible roots, x equals 0 or x equals 2. These are our two critical numbers, okay? Let's take a look at a graph of this function, right? So I want to remind us of what I just said a minute ago. These are the places we're going to look for extrema, but we don't know that they exist there because local extrema have to be critical points. Critical points don't have to be extrema. So let's take a look at the graph. Here's the function f, right? So let's Remember, our two critical numbers were at 0, and there is the critical point. When you input 0, the output is 0 for our function. And there's the other one at 2. The input of 2 leads to the output of -4. What we see from this drawing, from this graph, is that one of them is a local extrema. It turns out to be an absolute extrema, but it's also a local extrema. It's a local minimum, right? At x equals 2, we can see that that's the case. Meanwhile, at x equals 0, we do not have a local max or a local min, right? On the one side, the function is, on both, as we approach the function from the left, we're decreasing towards it, and as we pass it, we continue to decrease. So points to the left of that are greater than, so points to the left of 0 are greater function values, and points to the right of the origin have lower function values. So it's, that point is neither a local max or min, right? You can't find an interval around 0 where all the points are either greater than that or less than that, because on one side they're greater, on the other side they're less. Meanwhile, at x equals 2, we see that the function is decreasing towards 2 as we approach from the left, and then increasing as it goes away from 2 on the right. So to the left, all the functions are greater than 2, greater than the output -4, because they're decreasing to it. So they're all above, going down towards it. And then once we leave that point, they're increasing, so they're all above. So when we make our interval around x equals 2, right? If I make some interval, doesn't, in this case, it doesn't matter the size, but if I make some interval, all the points to the left and the right are greater than that. And so it's a local minimum, right? When we try that over here, all the ones on the left are larger, all the ones on the right are smaller, and so it's neither. And so this starts to give us an idea of what we can do to tell if something is a max or a minimum. Notice what I said. The problem at 0 is that we're decreasing as we approach it, and we continue to decrease. Whereas when we approach 2 from the left, we decrease, and then as we leave, as we pass it, we start to increase. We turn around, right? So think about a max and a min. They look like, right? They're going one direction and then they go to the other direction, as opposed to that point that was neither can look like this, okay? So what we are looking for then is that our function go from, in this case, decreasing to increasing, right? That as we cross this critical number, the function goes from decreasing to increasing. Well, what does that mean in terms of the derivative? The derivative has to go from negative to positive. So let's draw a picture to highlight this. So if we have a local minimum, right? If this is some function g, here's our critical number c, the derivative g prime must be less than 0 on the left, because the function's decreasing. On the right, g prime must be greater than 0 because the function's increasing. And so this is what we can look for to find a local minimum. We start decreasing, then we increase. On the other hand, if we were looking for a maximum, what we would expect is that g prime would start out greater than 0. We're increasing to the maximum, and then we decrease as we go away. We go to lower values, right? So to the left, in the case of a maximum, we have a positive derivative, and on the right, we have a negative derivative. Let's see if that works out with this function we just looked at, okay? So our derivative, remember, was f prime of x is equal to 3x squared times, where did it go? X minus 2. That was a good way to look at our function, our derivative. Let's make a number line here. Remember what our roots were for this, the critical numbers, the zeros of this. we're at 0 and 2. Let's look at the sign of the derivative. There's this chops up the number line into 3 regions. Let's look at regions. Let's look at the sign of the derivative. If x is less than 0, then 3x squared is going to be positive. 3x squared is always positive unless x is equal to 0. But we're not looking at 0, we're looking below 0. So this thing is always positive. If we're less than 0, we have a negative number minus 2. We get another negative number. We have a positive times a negative. F prime must be negative. If we're between 0 and 2, right now in this middle region, we're not at 0, we're not at 2. This first term, again, always has to be positive, right? 3x squared is going to be positive no matter what, because that's square. But if our x value is less than 2, x minus 2 is negative, we get a positive times a negative, we have a negative again. Right? But then, if we get bigger than 2, that first term is still positive. Sorry, the first factor is still positive. The second factor, x minus 2, now x is bigger than 2. It's positive. We have positive times positive. We have a positive sign on f prime. So, remembering the fact from up here, the positive derivative is increasing, the negative derivative is decreasing. When we went through the critical value 0, we started out decreasing, we continued to decrease, right? We were going down, we hit a 0 of our derivative, but then we continued to decrease. We had no minimum or maximum. But when we went from negative to positive at the next critical number, it means we went from decreasing to increasing. We know that critical number is a minimum. And we know that if we had the opposite situation, if we had a function where we were increasing and then decreasing, we would have a local maximum, right? Let's look at a quick example of that kind, and then we'll summarize what we have here. Let's look at the function g of x. Let's make this, well, let's just make it simple. We'll make it negative absolute value of x plus 2, right? So a quick sketch of this. This function is going to look like it's a flipped absolute value function raised 2. So it's going to look something like this. Okay. Now notice we can just look at the graph to determine what g prime looks like. G prime is going to be a piecewise function. On the left-hand side, it's the slope of this line is positive 1. So if x is less than 0. And as we go to the other side, the slope is negative 1 if x is greater than 0. Okay? And also notice we have no derivative at that corner, right? We've looked at this before. At these corners, we don't have a derivative. So what this tells me is a critical number, or the only critical number for g of x, is x equals 0. That's where the derivative doesn't exist. And we know at this point, as we cross over 0, the derivative goes from positive to negative. We're increasing as we approach this point, decreasing as we leave. That is a local maximum, right? So another example with a critical number, and what we look at is, does the sign of the derivative change as we pass through, right? We're going positively through x values. Does the sign of the derivative change at that critical number? And if it does, we must have a local extrema, a local max or a local min. It depends on which way we go, right? If we go from positive to negative, we have a local max. If we go from negative, decreasing, to positive, increasing, we have a local min. All right, so let's summarize all of this, and then we'll do one more example. So we can say that if, what do we have? If we have a continuous function, f, then we know that local extrema happen at critical numbers. Okay. And we now know we can't say critical numbers lead to local extrema, but now we know when they do. This is true if the derivative changes sign at the critical number. What I mean by that, let's be very careful, is on one side of the critical number, on an interval on the left, the derivative has one sign, and on the other side, the derivative has another sign. It might not be defined at the critical number. We're just looking on either side, does the sign of the derivative change? And then we can determine that the critical number is a local extrema. If it doesn't change, it's not a local extrema. And this gives us what we call the first derivative test. Okay. So suppose f of x is continuous on an interval containing the critical number c and f is differentiable on that interval, except possibly at c. Right, so like in that absolute value example, our function wasn't differentiable at that point, but nearby it was. If this is true, then f of c satisfies one of the following. So there are going to be three things that could happen there. So let me put them over here. One, the sign of the derivative, so we'll say f prime of x is let's say symbols make this easier. F prime of x is positive when x is below c, and f prime of x is negative when x is greater than c. Right, this is all happening on this interval. So whatever points of the interval are below c and above c. In which case we have a local max, right? Because this means if the derivative is positive when we're below c, that means we're increasing. Negative on the other side, we're decreasing, we have a local max. Right? We could have the case that f prime of x is negative when x is below c, and f prime of x is positive when x is above c, in which case we have a local min. And then finally, we have the case where the sign of f prime of x is the same when x is below c and x is above c. Then there is no max or min. Okay, so one of those three things is going to happen. So as we approach c from the left, we're either increasing and then going to decreasing, we're either decreasing and then increasing. So we could be doing this, or we could be doing something like this, increasing and then continuing to increase, or decreasing and continuing to decrease, right? So mark what are our critical numbers on each of these ugly sketches. right? In the top two, we have a max and then a min, and the other ones we have neither. And that's our first derivative test. You can look at the derivative to decide what happens at this critical number. So let's finish with one example, and then we'll save the further tests for the next video. So let's look at the function h of x is equal to 2x squared over x squared minus 1. Let's find its critical numbers and then determine if they are local maximums or minimums. So we have h prime of x is going to be equal to, I've got to do a quotient rule, so I'll have 4x, derivative of the top, I leave the bottom alone. Then I take the derivative, well, I'll leave the top alone, 2x squared, and take the derivative of the bottom. That's 2x. And then, of course, I square the denominator. This is pretty ugly. Let's fix this up a bit. So in the numerator, I get 4x times x squared is going to be 4x cubed. But then I've also got 4x cubed at the end, negative, so those are going to cancel, but then I'll have 4x times negative 1. So all of this ends up being negative 4x over x squared minus 1 squared. Okay, so there is my derivative. We need to know where this does not exist or where it's equal to 0. So where it doesn't exist, well, look at this derivative. It's a rational function, and rational functions exist on their domain. Their domains are everywhere except where there's zeros in the denominator. So this is h prime of x does not exist when x squared minus 1 is equal to 0. This, of course, happens. We can factor this to x plus 1, x minus 1, and get that x equals negative 1. Or x equals 1, right? So the derivative doesn't exist there. Notice our function doesn't exist there. So of course the derivative doesn't exist there. And then we can also see that h prime of x is equal to 0 when, well, let's just write it, negative 4x over x squared minus 1 squared is equal to 0. This, of course, only happens if the numerator is 0, as long as the denominator is not 0 at the same time. The numerator is 0 when x equals 0, which does not make the denominator 0, so we're good. So we get 3 critical values. So I want to take a look and see what's happening to the derivative at these points. Okay, so what I like to do, what lots of people do, is some version of this, a little chart. I'm going to make a number line with my 3 critical points. Negative 1, 0, and 1. And I just want to think about what's happening to my derivative in, well, now there's 4 quadrants, 4 intervals that these critical numbers have divided the number line into: below negative 1, between negative 1 and 0, between 0 and 1, and between 1 and infinity. I want to see what happens to the sign of my derivative in each of those regions. So let's remember, here's our derivative. If x is less than 1, so in this first region, well, then that means, sorry, if x is less than negative 1, well, let's make one observation first. As long as the denominator is not equal to 0 at 1 and negative 1, and we're not going to look at those points, we're only going to look between the critical points. So for all the rest of the numbers, that denominator is always positive. So the only thing that's going to tell us the sign of the derivative is the sign of the numerator. When it's positive, the whole thing's positive. When it's negative, the whole thing's negative. So if I'm in this region where x is negative and I'm multiplying some negative number times negative 4, I'm going to get positive numbers. If I'm between 0 and negative 1, again, I'm taking negative numbers and multiplying them by negative 4 and getting positive numbers. If I look at between 0 and 1, where I'm putting in positive numbers, multiplying them by a negative, my numerator is negative. And then for big positive numbers, multiplied by a negative number, we get a negative number, and the numerator is negative, and the whole thing is negative. So the derivative starts out positive at the critical number -1. It doesn't exist, but then it continues to be positive on the other side. Then it switches to negative at 0, and then remains negative after we pass through 1. So what does this mean? Well, let's look at our first derivative test. Suppose f is continuous on an interval containing the critical number. Let's start there. F is not continuous near -1 and 1. Those are asymptotes for, sorry, in this case, h. A function is not defined there, so any interval that contains 1 or -1, h is not continuous there. So we can't even use those critical numbers to look for a max or a min. So we're thinking about the critical number at 0. F is differentiable at 0. So we do have that, right? That was the critical number where it was equal to 0. And we satisfy one of these three things. At 0, we go from positive, the derivative goes from positive to negative, right? We start out positive, we go negative. That's case 1. F prime is greater than 0 when we're below C, in this case, C is 0, and we're negative when we're above C, we have a local max. In other words, whatever h looks like as it approaches x equals 0, it's increasing, and then after x equals 0, it's decreasing. We've got some kind of local max, okay? Now, there's a lot more work we could do to figure out a lot more about this. For instance, it's easy enough to see the value of h at 0 is 0. So I know my drawing's wrong. It would be at the axis, we must be increasing and then decreasing. We'll get into more about how we can use this function to determine derivatives to determine the shape of this graph. But what we found now is this first derivative test told us we have a local maximum. So because, let's say it this way, h prime of x is less than 0 if x is less than 0. And h prime of x is greater than 0 if x is greater than 0. I should really say, sorry, let me be a little more careful because it's not that way forever, but it's between -1 and 0, and then it's going to be from 0 to 1, that it's now negative. We have a local max at x equals 0 of h of 0 equals 0. So the local max in this case has a value of 0 as well as an input of 0. So let's finish by looking at a graph of this. This here is, no, here's h of x. Let's make this bigger. So we see our two asymptotes. You can see the graph not passing through -1 and 1, right? Looks like we're going off to positive, negative infinity, depending on how we approach it. But the point we care about is right there at the origin. You can see that this is a local maximum. As we approach it from the left, we're increasing. We have positive sloping lines. Let's look at those. Here we go, right? So here's our tangent lines that have positive slopes. As they hit 0, the slope is 0, and then they become negative sloping lines, so a negative derivative, right? So we go from positive derivative to negative derivative, and you can see that by the slopes of these tangent lines. Okay, that's enough for this one. We've got a lot more detail to go through, but this is a good start. Thanks, everybody. I will see you next time.